Here we discuss the second derivative test. Now we are familiar with the relative extrema of functions. If y is equal to f of x is a function given, then how do we find the points where it is having relative maximum, relative minimum? See here, this function is having relative maximum at the point b and relative minimum at the point c. So when we say this point B is a point where this function has relative maximum. A function f is said to have relative maximum or also known as local maximum at the point B if fx is less than or equal to fb for all x in some open interval containing b. That means if you take any open interval is containing b, you can see that whatever x if you take in this interval, the corresponding f of x if you calculate, that will be less than or equal to f of b. Every f of x is less than or equal to fb for all x in the neighborhood of b. Then we say this point bfb is the maximum point, relative maximum point, and the value fb is the maximum, relative maximum value. Similarly, this function is having relative minimum at the point C. If fx is greater than or equal to fc for all x in some open interval containing C. Here C is a minimum point here. You take any neighborhood of C, you can see that every x in this neighborhood has the property that fx is greater than or equal to fc. Now we observe this picture. In this graph, you can see that there are many maximum points, similarly minimum points. So this is a maximum point since in this neighborhood, every f of x if you calculate is clearly less than or equal to f of a. Similarly, at b also it has a minimum point. If you take any x here in this neighborhood of b, then that fx is greater than or equal to fb, and this is a maximum point. This is also a maximum, minimum point. So this function has two maximum points and minimum points. But there are a little difference here. Now at this point, tangent exists, derivative f dash exists, and f dash x is equal to 0 here. Here also the tangent exists at this point, and its slope is equal to 0. So f dash at b equal to 0. But at the point C, it has got maximum point. It is a maximum point, but here there is no tangent. Tangent does not exist. That means f dash does not exist here at this point C. It's a minimum point. Here also f dash does not exist. So normally this local extremum, whether it is local maximum or relative minimum, they occur at the point where either f dash x is equal to 0. So this is the point where f dash a is equal to 0, and this is the point where f dash b equal to 0. But here f dash c does not exist, doesn't exist. Here also this f dash d doesn't exist. So normally a function has local maximum or minimum, relative maximum or minimum at the point where either derivative equal to 0 or the derivative does not exist. So this is what is Fermat's theorem. By Fermat's theorem, if a function y equal to fx has a relative extremum at some point x equal to c, then f dash c equal to 0 or f dash c does not exist. So this is only a necessary condition. If fx has relative maximum, then either f dash will be equal to 0 or f dash c does not exist. Here, f dash c equal to 0 or f dash c does not exist doesn't indicate the function has relative maximum or minimum. Even without having relative maximum or relative minimum, f dash c can be 0 or f dash c may not exist. So how do we find whether this is relative maximum or this is relative minimum. But we can say that if f dash c happens to be 0, then we can say that either it has a local maximum or a local minimum. But how do we identify whether it is local maximum or local minimum? For that, we use the second derivative test. What is the second derivative test? Suppose f has a continuous second derivative on an open interval AB. Here you see the graph is continuous in the interval AB, and C is a critical point. Critical point means the points where either f dash C equal to 0 or f dash C does not exist. Here this is a critical point. This point C is a critical point, and here f dash C equal to 0, tangent exists, f dash C equal to 0, and here it is having local maximum. So this function has local maximum means the function actually ceases to increase and begins to decrease. Such a nature it has got, and therefore it is concave downward. It is concave downward, and therefore its second derivative f double dash x must be negative in this interval AB. So in the interval AB, the curve is concave downward, and therefore its derivative, second derivative is negative. So at the point C, f dash C will be negative. So if it is a C, x is equal to C is a local maximum point, relative maximum point, there f dash C will be 0 and f double dash C will be less than 0. This is how do we identify the local, the point is whether it is local maximum or not. At maximum or minima, f dash C will be 0. At maximum, f double dash C is negative. So, if f is a continuous second derivative on an interval AB containing a critical point C, then if f double dash C is negative, then f has a relative maximum at C. Similarly, if f double dash C is greater than 0, so here you can see that this curve is having local minimum at the point C. The tangent is parallel at C, that means f dash C equal to 0. So at local minimum, f dash C is 0. But this curve is, we can see that it is ceases to decrease and begins to increase if you consider the portion of the curve around C, or in a small neighborhood AB containing C. If you consider, you can see that the function is stopping to decrease and beginning to increase. So this curve is actually concave upward, concave upward. Since the curve is concave upward, its second derivative must be greater than 0. So in the interval, if you calculate f double dash x, that f double dash x is greater than 0. So C is a point here in this interval, and therefore f double dash is greater than 0. So C is a local minimum or relative minimum of the curve y is equal to f of x if f dash c equal to 0 and f double dash c greater than 0. So this is how do we identify. So whenever there is f double dash of c greater than 0 and where f dash c equal to 0, we can say that this c is local minimum. Whenever f dash c is equal to 0 with the f double dash c negative, you can see that c is local maximum or relative maximum point. Relative maximum point, here the relative minimum point. But if f double dash c happens to be 0, we cannot say anything about the point, whether it is having maximum or minimum or point of inflection, we cannot identify that. So if f double dash c equal to 0, then the test is inconclusive. See here, this is the point where f double dash c equal to 0. F double dash c is equal to 0. Actually, this is a point of inflection. The curve actually changes its concavity, that is from concave upward to concave downward. So this point is not a local maximum or local minimum, but this point here, it is point of inflection. Now find the relative extrema of fx is equal x cube minus 3x squared minus 24x plus 32. using the second derivative test. See, this is the graph of the function. Second derivative test. Using second derivative test, you have to identify the extremum points. Find fx, f dash x, and f double dash x. The relative maxima or minima occurs at the point where f dash x equal to 0. So putting f dash x equal to 0, you get 3 into x minus 4 into x plus 2 equal to 0, which gives you 2 points, x is equal to 4 and x is equal to minus 2. That means 4 and minus 2 are the critical points, and there may be local maxima or local minima. We have to calculate f double dash at this point. So calculating f double dash at 4 and minus 2, you can see that f double dash of minus 2 is negative. That means this minus 2 is a point where this function is having local relative maximum. And since f double dash of 4, if you compute, you can see that it is plus 18, which is a positive number. That implies this x is equal to 4 is a point where this function has a relative minimum. So to find the relative extrema using second derivative test, you need to compute f dash of x and f double dash of x. Putting f dash x is equal to 0 gives you critical points, and these critical points may be relative maxima or relative minima. To identify whether it is relative maxima or relative minima, you calculate f double dash x at these points. If f double dash x is greater than 0, you can conclude that that point x is relative minima. Similarly, if f double dash x is negative, then you can say that this x is relative maxima. That is, x is a point where this function has a relative maxima. Now, the second derivative test is not useful if f double dash equal to 0. You see these pictures. Here in all these cases, in the case of fx is equal to minus x raised to 4, or fx is equal to x raised to 4, or fx is equal to x cube, or in all cases, f double dash is equal to 0. Here you can see that it has, whether it has local maximum or not. Here it has local maximum at this point. This is the maximum point. Even if f double dash is equal to 0, this function has local maxima at this point. Here also f double dash is equal to 0. It has local maximum. But here f double dash is equal to 0. But this function has no local. So for this function y is equal to x cube, f double dash c. What is f double dash c? At the point, you calculate f dash of x, which is 3x square. f2x is 6x, which is equal to 0 when x is equal to 0. That means at x is equal to 0, this f2x is 0. But this is not a point where this function has a relative extremum. It's not a relative extremum point. So the function is unbounded. This function has no relative extremum or absolute extremum. But here f double dash x is equal to 0. If you take fx is equal to x raised to 4, clearly you can see that f double dash x is equal to 0 gives you x is equal to 0. So x is equal to 0, at x is equal to 0, f double dash x is 0. So this is a point where f double dash is becoming 0, but the function has local extremum. That means it is a local minimum. It has a relative minimum at the point. All the values of the functions are clearly greater than or equal to 0. That every f of x is greater than or equal to f of 0, and therefore 0 is a local minimum point. Here you can see that every f of x is less than or equal to f of 0. f0 is the maximum here. So 0 is a local maximum point for this function of y is equal to minus x raised to 4. So for these two cases, all the cases f double dash is equal to 0, but in some situation it has local maximum or local minimum. But in certain case, this function may not have extremum point. Now find the relative extrema, if any, of the function using the second derivative test. So let us take a problem. One, let us take. Let it be ht is equal to 37. The question we are doing. ht is equal to 1 by 3 t cube minus 2t square minus 5t minus 10. So we are going to use the second derivative test for identifying the extremum points. So first to get the extremum point, for that you need to find h dash t. H dash t is equal to 1 by 3 into 3tq, that is t square minus 4t minus 5, and h double dash t is equal to 2t minus 4. Now h dash t equal to 0 gives you certain points where the function has critical points. So t square minus 4t minus 5 is equal to 0, and this when you factorize you can see that is t minus 4 t minus 5 into t plus 1 is equal to 0, which implies t is equal to 5, t is equal to minus 1. So this minus 1 and 5 are the critical points, Normally extremum points occur at the critical points. So you calculate f double dash of minus 1 and f double dash of 5. See the sign. F double dash of minus 1 is 2 into minus 1 minus 4, which is clearly negative, which indicates x is equal to minus 1 is a point where this function has the relative maximum. Similarly, f double dash of 5 is equal to 2 into 5 minus 4, which is clearly greater than 0. This indicates x is equal to 5 is a point where this function has a local minimum. So this is how do we calculate the relative extremum and relative maximum and relative minimum. So what you have to do is, if the given function is y is equal to f of x, identify the critical points. That means putting f dash x is equal to 0 gives you certain x. These are the critical points. At these points, you calculate f double dash of x. If f double dash of x is greater than 0, that x is a point where this function has local minimum. And if f double dash x is less than 0, this function is having local maximum at the point x. This is how do we identify the extremum points. Now, the roles of f dash and f double dash is determining the shape of the graph. We can identify whether the curve is concave, downward, concave, upward, whether it has point of inflection. These are all got by calculating the first derivative and second derivative. The first derivative test, second derivative test. Using this first derivative test and second derivative test, we can identify whether this function is or what is the shape of the graph of the curve. We know if f dash x is increasing, f dash x is greater than 0, at the point x clearly function is increasing. If the second derivative is greater than 0, the function is concave upward, like this, concave upward, and the function is increasing. Like this, it is increasing and it is concave upward. If f dash x is greater than 0, the function is increasing, and f double dash x less than 0, then the function is concave downward. So it is a function is increasing like this, but it is concave downward since f double dash x is negative. Similarly, if f dash x is less than 0, function is decreasing. F double dash x greater than 0, the function is concave upward. So it is function is decreasing, and at the same time it is concave upward, and this curve is decreasing and it is concave downward. For that, f dash x will be negative and f2x second derivative will be negative. So identifying this f dash x and f double dash x, we can see how is the shape of that curve within a small interval, whether it is increasing, decreasing, or it is concave upward or concave downward. So this is the how we determine the shape of the curve by using first derivative test and second derivative test. So with this, I conclude the session. Thank you. We'll be meeting with another session. Bye.